So right now we're going to focus on this part 2 and use it to compute all these applications that involves definite integrals, and can understand this part 1, the existence and computability of that thing, almost towards the end of the semester. But it is important you understand that part. It's used somewhere in higher parts. So right now we're focusing on applications of fundamental theorem of calculus. So last time we did this motion problem. After that, they introduced area between curves. And after that, they introduced average values. And in Calc 2, you learn more techniques and more applications of physics and geometry problems. So here's the idea, and I'm going to review that idea on what happened with our motion problem. Idea was that you have problems from geometry, from physics, such as motion problem, and engineering problem, all that. You analyze it, and you try to write those down in terms of mathematics you understand, and you'll suddenly realize that you have to add up these million terms that looks just like a Riemann sum. Whether it's a graph under, area of a curve underneath a area of the region bounded by the curve or not, if you look at it as a mathematical expression that look like Riemann sum, then you can use definite integral to calculate that sum. That's the idea. So let's look at Riemann sum again. Riemann sum looks like this. Any tiny quantity delta xk multiplied to f of xk star, which is not so tiny. If you remember how the calculation goes in the table of f value, they're not small. There could be 8. This f of x star, k star can be 5, but delta xk is usually very, very small. So if you multiply this one, this is very, very small number, because if delta xk multiplied to tangible side is a small number. But we add many, many times, right? Think about the triangle, which I showed you in the very first class of the semester, down there in length of that zigzag line. And if you ignore that little thing, they might add up to the significant amount. So you can't just say that this one will be, because it's 0, tiny amount, all this sum ends are very small, therefore it's 0. You can't say that because you're adding so many times something. Those tiny errors might add up. That's why they analyze this one carefully. So here's a motion problem. Though the analysis went like this: Vk in certain moment at time tk is a velocity multiplied by the interval of time that represent tiny displacement over a very, very short period of time around that time period tk. So what this vtk times delta k measures in physics is very, very small displacement. If you add all those displacement together, that must be good approximation of the total displacement that happened, from the time period A to B in that context. So that's a Riemann sum. That's the physical analysis. It looks like a Riemann sum. Here's one thing, all in terms of tk multiplied by tiny interval delta k. So you can enter this finite Riemann sum symbol becomes this stretched integral symbol from A to B. Vtk becomes Vt. This delta t changes to symbol dt, right? And you know how to calculate this thing using fundamental theorem of calculus, part 2. So that analysis physics, and you enter area underneath the curve because this happened to be the Riemann sum. All right, so that's how it typically goes. And I'd like to introduce